Hey, bada. Oh, son of. Man, I would not want to get hit by a fastball. Do you know that some pitchers can throw this thing 100 miles an hour? Did you know that nothing in modern physics can tell you what happens when you throw a baseball? Not quantum mechanics, not string theory, not curvature of space-time, nothing. Basically, modern physics cannot tell you what happens when something moves. Well, let's fix that with this baseball. Now, the pitcher has a choice. He can throw the ball 50 miles an hour, or he can throw the ball 100 miles an hour. In either case, the pitcher must exert some energy. The ball carries that energy over to the batter and unloads it on him. Ouch. Now, obviously, it's harder to throw a 100 mile an hour fastball than it is a 50 mile per hour fastball, but how much harder? Would you think it'd be twice as hard since it's going twice as fast? And let me show you with these quarters. So let's say the pitcher's going to throw the 50 mile an hour fastball, and let's say it takes that much energy to throw the ball 50 miles an hour. Well, how much energy do you think it would take to throw two balls 50 miles an hour? If you guessed 2 quarters, well, you'd be exactly right. Pretty straightforward. But now let's say the pitcher wants to throw the ball 100 miles an hour. Well, how many quarters worth of energy do you think it would take? It takes 4. Wait a minute, that makes no sense. Twice as fast, but 4 times the energy. Let's look at this carefully. So it took this much energy to get this ball from 0 to 50, an increase of 50 miles an hour, but it took 3 times as much energy to get it to go from 50 to 100, another 50. It makes no sense. Now, it's absolutely true, but it makes no sense. Now, you might be thinking about air resistance, but this energy relationship here has nothing to do with air resistance. It's as if the pitcher were in a spacesuit and he was throwing the ball in outer space where there's nothing else around. This is just the energy of throwing the ball. So the pitcher has to exert 4 times the energy to throw the 100 mile an hour fastball, and it hurts the batter 4 times as worse. Ouch. No wonder they get angry. Now, if we're going to solve this problem and come up with an answer, because modern physics doesn't have one, we're going to have to do a little math. Now, don't worry, it's real simple. Besides, I'm going to do it all, so all you have to do is sit back and watch. So the energy we're talking about here is called kinetic energy, the energy of an object moving. So in our situation, the mass is the baseball. V, velocity, is how fast the ball is moving, either 50 or 100 miles an hour. So let's put the numbers in for our 2 situations and compare the results. So here I put a 1 in for the mass, the 1 baseball, and here are 2 different speeds, 50 and 100. And there it is, 4 times the energy in a 100 mile an hour fastball. But where did we get this equation in the first place? This equation came out in the year 1687 and is what's called an empirical equation, meaning we know this relationship from experimentation only. Perform a bunch of experiments, plot the results, and out comes this relationship. We know this ball transfers the energy from the pitcher to the batter, but how does it physically do that? And why does it do it according to this weird relationship? To understand what I mean by physically storing energy, let's look at another way this ball can store energy, and that's heat. So let's leave this ball at room temperature, 70 degrees. And we'll take this ball, we're going to stick it in the oven for a while, and we'll bring it back out on the table, and the ball is 200 degrees. So what is the physical difference between these 2 balls? Yeah, this one's hotter, right? Yeah. Well, these balls have a structure, okay, made up of molecules, and those molecules are always moving. And the physical difference between the 70-degree ball and the 200-degree ball is that in the 200-degree ball, the molecules are moving more. So what we call temperature is actually a measurement of mass moving, the molecules in the ball. They never disconnect, but they move a lot more. That's what's called heat. Back to kinetic energy. Again, it's energy in molecules moving, but it's not the molecules of the inside the ball moving within the structure. It's the atoms and molecules moving through space. Well, if you're going to solve a problem, it's best to focus on where the problem is. Okay, so in our situation, we only have two things. We have mass and velocity. Well, mass is the ball. Well, two balls, twice the energy. Makes perfect sense. No problem there. Let's look at velocity. Now, twice the velocity, 4 times the energy. It makes no sense. Absolutely true, but makes no sense. So there's our problem. Our problem is really this little square thingy. Okay, I mean, if the equation was 1/2 mv, then twice the velocity would be twice the energy. It would make perfect sense, but it really is this way. And so let's figure it out. And when you don't have anything to go on, well, let's just throw out everything we can think of about this ball moving. When the pitcher throws the ball, it goes a certain distance. We'll put that up there, measured in feet. Well, this ball has a surface area. We'll put that up there, measured in square feet. The ball has a volume. Well, so we'll put that up there, measured in cubic feet. Well, it takes time for the ball to get from the mound to home plate, so it doesn't get there instantly. So let's throw time up there, measured in seconds. Oh, the ball has atoms and molecules. Might as well put that up there. I'm done. That's all I can think of. It's just a ball moving. So now let's look at what we got. So if you just had to pick something, I mean, we're trying to figure out this little square thing. So if you just had to pick something, not knowing anything else, what would you choose? Take a second and think about it. Well, if you chose that, well, I'm with you. It makes perfect sense. Surface area works. Well, before we get too excited, let's go back and review our other options. So if the pitcher were to throw the ball in space, the ball could go a mile, 1,000 miles, 1,000,000 miles. As long as nothing interfered with it, it would continue on at 100 miles an hour. And when it hit the batter, it would unload the same amount of energy no matter how far it went. So distance is out. All right, what about volume? Well, if the ball stored kinetic energy volumetrically, well, then our equation would be 1/2 mv cubed, but it's not. It's 1/2 mv squared. So you could also, I guess, take the distance divided by volume, come to square. But as we said earlier, distance doesn't matter, so volume is out. Okay, what about time? Well, like distance, pitcher throws the ball in space, it doesn't matter how long it travels, as long as nothing interferes with it, it's still going 100 miles an hour. When it hits the batter, it's going to load the same amount of energy, whether it traveled for a year, 1,000 years, 1,000,000 years. As long as it's going 100 miles an hour, so time is out. Okay, what about atoms, molecules? Well, that's mass, and as we already said, twice the mass, twice the energy makes perfect sense, so mass is out. So surface area works. Not only does it works perfectly. But it's not the ball's surface area. I could have a lead ball with the exact same mass as the baseball, and they would both store kinetic energy in the same amounts, but the lead ball would have a lot smaller surface area. Don't give up. We've come a long way. For right now, though, we need to talk a little bit about surface areas. Boring, I know, but it's necessary. So here I have a butcher's block, and it has a surface area, but it also has quite a bit of thickness. So here I have a piece of poster board. Well, it has the same surface area as the butcher's block, but it's a lot thinner. So the poster board is a better representation of a surface area than the block. the surface area we're looking for is very, very thin. You can't have a perfect surface areas because it have zero thickness and it wouldn't exist in the first place. But what we're looking at is some surface area very, very thin, but still with a little thickness. So really what we're looking for is, it's more of a layer. So it's not the object surface area that stores kinetic energy. It's a layer that's formed when an object moves that stores the energy. Now, so far, this idea of a layer is just an idea, but I've come up with a way to physically detect it, to prove it's really there. A physical layer where quantum mechanics happens that stores the kinetic energy of a moving object. At the end of this video, I'm going to show you how to detect it, but unless I explain a few things first, you won't understand the detection process. So hang in there a little bit. So we're saying that when this ball moves, a very thin layer is formed. But formed in what? Well, here's where you got to know a little about the history of physics. Don't worry, I'll keep it simple. For hundreds of years now, it's been generally understood in physics that there's something, well, everywhere. In the old days, it was called the ether. Then along came Einstein, it was curvature of space-time, and then there was string theory, and now there's quantum mechanics, standard model, quantum field theory, but none of them tells you what happens when an object moves. So why should you think that there's something else? Okay, well, it's easy. Okay, you can go out in your yard, place a mark in the yard, and then try running up to it and stopping right on the mark. From a full run to a dead stop right on the mark. Well, you can't do it. Because what will happen is your body will continue to move forward whether you want it to or not. Well, it's not you making your body move forward, you're trying to stop. So what does make your body move forward? To something else. So if something physically exists, one thing I know as an engineer is it has a structure. Anything that's real and physically exists has some sort of structure. This ball, this table, molecules of air, even atoms have a structure. Engineers, structure, it's kind of what we do. And another thing I know as an engineer that when something with a structure moves through something else with a structure, a layer of interaction has formed. And NASA has almost shown us the layer we're looking for with an experiment called Gravity Probe B. $750 million of your tax monies went into Gravity Probe B, so let's take a look at it. Gravity Probe B was designed to prove something called frame dragging, or the lens-thering effect. Basically, that when the Earth rotates, it drags around space-time with it. Can you see the layer we're talking about here yet? So think about, while the Earth seems massive to us, in the scale of the universe, it's just like a little speck of dust. I mean, our own sun is 1,000,000 times bigger than the Earth, and there are billions of suns out there, and there are billions of galaxies. So do you think this tiny little speck of rotating dust could rotate the space-time of the entire universe? No, just a portion of it. Okay, so think about it. If this part rotates and this part doesn't, well, what do we have to have here? A layer of interaction. Now, Gravity Probe B did not detect this layer. It just proved that this part was rotating. How will we actually detect that layer? Well, out in space, who would even know where to begin? But what about right here on Earth? Well, it's how I figured out the gyroscopic effect. For 170 years, nobody could figure out what happens when a wheel spins and rotates at the same time. But I figured it out. Well, how did I do it when nobody else could? Well, I took the idea of this layer and I applied it to the gyroscope's motion. And you could see some of that work in my video, Truth About Gyroscopes. But what I didn't explain in that video was the layer. So now I want to demonstrate the layer in action with the gyroscope. So here's the gyroscope just spinning. And these are the centrifugal forces being experienced by the wheel. Now, the only way you could maybe measure them is to stick a strain gauge on there, but the strain gauge would have to spin with the wheel. So the only way we can imagine these forces is if they were be spinning with a wheel. But watch what happens in precession. So here are the forces in precession. They're sinusoidal, but watch. So what I've proven with this is that the gyroscopic forces, while they do rotate with the wheel, they do not spin with the wheel. So how can these forces be created by the spinning wheel but not spin with it? If there's a physical layer between this wheel's rotating space and the observer's space out here. So we've got a layer with gravity probe B, we've got a layer with a gyroscope, and we've got a layer with the baseball. But all that is not good enough. We have to be able to detect it. Here's how I've come up with the way to detect it. Light is probably the only thing sense enough to be able to detect the layer. So here I have a powerful light source, maybe a laser. Out of it shoots two beams of light. Here we have a giant iron wheel, and around it are some mirrors. And so the mirrors reflect one beam of light in this direction. On the other side, the mirrors reflect the other beam of light in the opposite direction. Both beams of light come out and be directed to what's called an interferometer. Now, an interferometer measures light wave interference. They're used in ring laser gyroscopes. So you'd set this whole thing up with the wheel not spinning, and then you get the wheel spinning. And the idea is that the light traveling with the wheel's spin of direction should come out and arrive at the interferometer sooner than the light traveling against the wheel's rotation. So yes, the light would be traveling at the speed of causality within the rotating space of the wheel. This is similar to the Michelson-Morley experiment, but why did the Michelson-Morley experiment fail? Because Michelson and Morley didn't know this was happening. The Earth was dragging its relative space around with it, and this wheel should do the same thing. While this experiment sounds really simple, it's not. There are 100 engineering problems to resolve. Like, how big should the wheel be? How fast should it be? Vibration from the spinning, affecting the mirrors, adjustment of the mirrors. Should it be done in a vacuum? There are a million things to resolve on this experiment. But it is a way. Now, but I'm only one guy. I mean, there are thousands of physicists out there, some of the smartest people on the planet. Maybe they can figure out another way, a cheaper way, a better way. Okay, so finally, a physical demonstration of the layer in action. So here are two empirical equations. Both came out in 1687, and I used just this one to explain the gyroscopic effect. So now let me show you how the layer works with both of these. So here's a rough demonstration of throwing the baseball. So the pitcher applies force to the baseball, space provides a resistance, the layer is formed, the layer carries the baseball, storing the kinetic energy, and then loads it onto the batter, just like in real life. But straight line motion, that is the simplest motion you can get. So you really you couldn't, it works, yeah, but you really couldn't draw any conclusions from it. But watch what happens when you take the layer and apply it to the gyroscope. Some of the most complicated motion that you'll see. So first thing you notice about this model is the springs are arranged differently than with the baseball. Well, the baseball is a symmetrical object. So think curvature of space-time. The baseball would affect the space around it symmetrically because, well, it's symmetrical. A wheel is not symmetrical, so it would affect the space around it differently. The largest effect is out here on the edge, and the springs are pointing, just like space, down into the axle, evenly in all directions. So let's say you want to accelerate the wheel by spinning it. Well, space would provide the resistance. Well, try to spin it the other direction, space would resist the other direction automatically, just like in real life. But now, here's how I figured out the true forces on the gyroscopic disc. So, when a wheel is spun and rotates at the same time, these are the forces on the disc, on the wheel. They're sinusoidal, and they will reverse here with, say, a reverse of rotation. They'll reverse spin also, but this is just, here we're just reversing rotation. So watch what happens when the wheel is spun and rotated. What do you see? A sinusoidal pattern of forces, just like in real life with a gyroscope. Reverse the direction of rotation, the sinusoidal pattern reverses. Just like in real life. What happens in the layer? Quantum mechanics. Is the layer the best thing to explain these relationships that are over 300 years old? Well, yeah. I mean, they're the only thing. It's the only thing, because nothing else in physics explains these relationships. Does the layer exist? We won't know until we detect it. Whew, my brain's tired. Thank you for watching.